wanted to be able to explain this. Your slides take like 3 extra slides full of entirely words to get to this point. So I put what I care about on this slide, and then the picture we're gonna draw, and you guys still have the other slides. So you can see this explained in writing if you would like, but I don't want to look at all those words on the slide because that, I don't want. So, at cold temperatures, like really cold, in a dry ice and acetone bath, -78, you get mostly this product, right? At -15 Celsius, I don't know off the top of my head how you get to that temperature, you end up with mostly this product, right? The 1-2 addition. But if you do this, man, that's the wrong thing I copied. I put the exact same thing, but there is a thing. Here we go. This is what I wanted. There we go. At higher temperatures, we get this, mostly this one, and mostly this one. Why? That's what we're going to answer. So, that's why we're going to draw stuff. That's literally all I was looking for, that little sentence. And they made it, not even on a bullet point, they made it a sub-bullet point, so it was lost in the just way too many words they put on their slides. I don't like it. I mean, it's useful for you guys to go over afterwards because the way that I would make slides would probably be not overly useful for going back over later. But, okay, so, you guys have done, yeah, during time you do reaction coordinate diagrams, right? Okay, so, stop being terrible, please. Please stop being terrible. Okay, that's fine. All right, so on this side we've got energy, right? And I'm actually gonna do, usually we have like reaction coordinate is just how close are you to being done on the reaction, and like we never put anything down here, but usually this is considered, or like we draw products over here and that's considered 0, and then reactants over here. I'm gonna draw my products in the middle because we have, or reactants, and then products. I'm gonna draw my reactants in the middle because we have 2 possible products. So, we do, we're gonna call it, all right, so we've got this, and we've got 2 different products. One of them is our, so many things, here we go. One of them is our 1-2 substitution, right? And one of them is our 1-4 substitution. So, at cold temperatures, we favor this. At higher temperatures, like 40, 60 degrees Celsius, we favor this. We're gonna figure out why. But besides that, which one of these guys is more stable? Which one of these guys is just, like when I draw these product lines, which one is gonna be a lower energy? Like, which one is lower energy, more stable, gonna have a lower line over there?
10%, the bottom.
Yeah, right? Because this one, like, we don't really talk about having to stabilize halogens. They just sort of hang out where they want to, right? Like, I don't know, they just do things. But double bonds, they're less stable if they're on the end, and they're more stable if they're more substituted? If they have more substituents. Substituted, if they're more substituted. So, let's put 1-4 over here and call it this. We're still going to pretend that we added that. Yeah. There. we're still gonna pretend that we added deuterium bromide and not HBr because it's nice to have the other thing on there. And then we're gonna go, this one is here, bromine, deuterium. Or if we added Br2, then both of these are bromines. So, this one's lower energy, which would make sense. Why at higher temperatures at least, the results make sense, right? Because this one should be favored, right? I mean, it just looks like it should be favored thermodynamically. So, what else am I forgetting? What else do I have to mark before I just make a line like this? The other thing, I make a hill, right? And that's for,
Transition state.
yes, and that shows us how big our activation energy is. So we put our transition state. Now, this is, I'm gonna put them about there. And this is something that we have to, like, there we go. Okay. These guys, I don't think, as far as I know, you can't just like eyeball them or like decide what they're gonna be, like figure it out. I'm pretty sure, yeah, as far as I know, these guys are basically just, you do computational chemistry to figure out what the transition state is, which is really annoying, or you just sort of see which goes faster if you can, right? So, when we're here, when we have a high temperature, we favor the one that's more stable. That makes sense. When we have a high temperature, we are under thermodynamic control, right? So this is the thermodynamic product. In this case, because we have this drawn the way it is, because we know experimentally that at low temperatures we end up here, that means this must be the kinetic product. And the reason that at lower temperatures we don't necessarily reach equilibrium is because, it's gonna roll. Basically, if we cool it down enough, we can kind of cool it down so that like the amount of energy that sort of exists around, like in the atmosphere around this, is too low to reach this, right? Or like, you know, this one has a lower activation energy, so if we cool it down enough and make sure there's not enough activation energy to make this one happen, then we favor this, because we couldn't even get to the transition state of this, so we didn't get to make a whole lot of this. If we warm it up so there's enough ambient energy for anything to happen, and the transition state is not like kind of energetically unreachable, then we get this one. Now, we're not always, okay, yeah. So, in this case, kinetic product, thermodynamic product. If I were to give you just a reaction coordinate diagram, and honestly didn't even give you any chemistry, I just went, here is a reaction coordinate. Fine. Losing secret. Here's a reaction coordinate diagram. Goes up. Starting materials, and we've got product A. Well, okay, I guess we read this way. So this can be product B, this can be product A. And then I'm going to draw in all right, now which one is the, knowing nothing else about this reaction, which one's a thermodynamic product? A or B? Thermodynamic, right? Thermodynamic is more stable, so we're gonna have B. energy in the world is available, and it can do either reaction freely, and, you know, reversible or has the ability to kind of, is not as aggressive as like Grignard, where it's just like, nope, too fast, then we're gonna be able to favor B, right? If we cool this way down, are we eventually going to, should we eventually be able to cool this down enough that we start favoring A? No, right? Because this is not the kinetic product. The kinetic product is not always the product that is higher in energy, or just the other one, the one that's not the thermo product. In this case, this is the thermo and the kinetic product. So if you're under thermodynamic control or kinetic control, you should end up with this guy. And if this is your desired molecule, you should probably pick a different reaction or something to get there, because this is not ever going to favor that. And to figure out, so for thermo, it's whichever one's lower, right? Let me write kinetic in a different color so I can color code these. Whichever products are lower energy, more stable. For kinetic control, it's which activation energy is lower, right? Does that make sense? So sometimes thermokinetic, sometimes thermo and kinetic. Yeah. All right. Yeah, we've already talked about all of this. Yeah, so here's, in some cases, the other one's more stable. So it's not always 1,4 addition that is the thermodynamically favored product, right? You might have other substituents on there that make it so that your 1,4 addition results in a substituted double bond, but your, but your 1,2 addition is actually more substituted double bond. So that's why it's not just a straight 1,4 addition is the thermodynamic product. It's dependent on those things. All right, UV vis spectroscopy. We're gonna do, it's fine. Okay, UV vis spectroscopy we're gonna hit pretty quickly, but basically, you guys have done this, well, you did this a little bit in Gen Chem, you did some Beer-Lambert law, and most of the time you use like salts or something containing a metal, because if you wanna get colors, metals are the easiest way to get them. You can get all sorts of colors with metals, because they do funny things with their energy gaps. But, in our case, we're talking about organic, so different things with the energy gap. All right, your absorbance is equal to log of I naught over I, the intensity of the radiation on the sample over the intensity that's actually transmitted through, right? So no sample, how intense is the light? Sample, how intense is the light? This is no sample, this one is sample. So that's why absorbance over 1 is like not a thing. If you start getting absorbance over 1, it's like, it's not valid, right? Because you're not talking about like 100% transmittance is absorbance 1, right? Log of 1 is 1? Is that how that's work? Yeah, maybe?
No.
No. Shit, what is it? It is. Is it?
Oh,
No.
yes.
Log 1. Oh, log of 1 is 0. Oh, yeah, if they're the same. Okay, yeah. Log of 1 is 0, because if those are the same, that doesn't mean we're absorbing all of it. It means we're absorbing, like, none of it.
Do you need to like memorize that for you to get an exam? Or will it just be like, that wouldn't
I think on exam 3 I had a question like that, so I just threw it on there, but no, that's dumb. I hate memorizing equations. Like, let me tell you, I've been doing the chemistry for like 7 years now. So I did 2 years as a master's student, and I've been here. This is the end of my 5th year. And let me tell you, the things you don't have to memorize, a lot of them. And things that are useful to memorize, you just end up accidentally memorizing them anyway. So, that's absorbance, whatever, it's a thing. So, this is a nice little UV-Vis spectrum for, what is that, 2,5-dimethyl 2,4-hexadiene. And we have the every other pattern of double bonds, so this is conjugated. So we've got some absorbance right there-ish. Basically, it's not super useful yet, but like it looks like this. Unlike NMR, where we get like peaks, right? In NMR we get peaks, and in UV-Vis, or in IR, we usually get peaks, right? Unless we have like hydrogen bonding and then they're kind of wide. And then UV-Vis, they're like wide, like you don't get specific numbers, you get like rolling hills, which we're gonna talk about in a second. Beer-Lambert law, you don't have to know this. What you should know is basically absorbance and concentration. Absorbance, concentration, the length of the sample cell. So you guys get a linear relationship between absorbance and concentration when you use the same compound, right? So your molar absorptivity stays the same, and the length of your sample cell, your cuvette, is the same, right? So how much of this stuff the light has to travel through. Whatever. Okay, the light that you see is the combination of the reflected wavelengths. So, we see around 400, or in that general area, 400 nanometer light. It looks purple to us. We see 750, not, oh, 650, no, not 650. This, I don't think this is accurate, because I'm pretty sure 400 isn't the UV by a bit. But we see, these are the color wavelength correlation. So if we had a light, like an LED, and it's like, hey, I am a 650 nanometer light, it's over here in the reddish orangish area. If we have a light and it's like, hey, I am giving off light that is 450 nanometers, then it's gonna look bluish purplish, right? That's if a light is shining that wavelength at you. When we're talking about absorption, we don't see what's absorbed, we see what's reflected, right? So if we see something that looks red, or in the range of yellowish, we're absorbing down here, right? We start looking like kind of yellowish to orangish down here if we're only absorbing here. We start absorbing a little more, and a little more of that blue gets absorbed, and we start looking reddish. And then if you want to get to like purple or blue or even green, you're having to absorb like green opposite. Green is the opposite. So whatever. You want to start seeing green, you have to absorb like everything except red, right? So these are like the easiest colors to reach. And with metals, you can get all sorts of colors, right? With organic compounds, we get a whole lot of white and off-white and yellowish and like orangish. And if you're really lucky, like a deep orange, maybe a red. And that's because we don't have the same band gap changing as these. So, all right, let me just go to, this is what I wanted to show you. So this is, have you guys seen something like this before? Have you seen maybe, I'm trying to remember if in Gen Chem they do anything with just like So a simple version of this is just let me do it's like okay, so the main lines here, let me make them a different color. I can find a different color, but I keep hiding myself. These blue lines, these are electronic, stop hating me, electronic transition states. You are no longer going to be stored face up. So this you get between these by promoting an electron to a different orbital, right? And we talked about how we had the HOMO-LUMO orbitals. So we had, let's see, 4. One of these numbers, please work. It's my fault for storing them upside down. Okay, for this guy we had 4 pi molecular orbitals, right? We had pi, these guys are anti-bonding, these guys are bonding. And we have, yeah. This is what it normally looks like, right? Because we've got 4 pi bonds, and this is how it is. Or 4 pi electrons, sorry. So they hang out at the lowest energy configuration, they make 2. Highest occupied molecular orbital, and we're talking about occupied at the ground state, so at its lowest energy situation, lowest energy state. Highest occupied is here, lowest unoccupied is here. These are the 2 we care about, right? And basically that's the difference between here and here, because this is what S0 looks like, and this is pi star. This is what S1 looks like. So we took an electron and we promoted it, right? It was here, now it's up there. So promoted it to a higher level, now we're in a higher electronic state. Yes? These little lines, these are just vibrational energies. So this is the reason that UV-Vis doesn't give you nice sharp peaks, because there are vibrational energies, so just because stuff vibrates around, S0 is like, I mean, here's S0, but also if it's like vibrating in this way, then like S0 is kind of in this range, or it's, you know, it can be kind of around here based on how it's flailing about in whatever situation it's in. So this is why we get broadband in UV-Vis. We don't actually have to care about these guys. I just draw them in so that we can see like the band broadening, the reason we've got that band broadening. So when we shine light, we do absorption, and we go up here, and we get to one of these guys. This measurement of this absorption, that is our, that's what we're measuring with UV-Vis. And there's a bunch more to this diagram, but I added it, not your book. And you don't really have to know the rest of it, because that'll be, that should be analytical stuff when you start talking about fluorescence and phosphorescence spectroscopy. But basically, a lot of the time we absorb somewhere in here, and then stuff shakes around to get generally down to the lowest excited state, or in our system crosses and goes over here. Don't worry about what that is. And then Usually it also just sort of shakes around and gets back to the bottom, and that's that. If it glows, whenever you shine specific wavelengths of light on it, then it's fluorescing, so it shakes around to get to here, and then it's like, you know what? I'm going to get rid of this last bit of energy by releasing a photon of light, so it does that. And then this is just, it's a similar thing. It looks the same, or similar, but like glow-in-the-dark stars, like it takes longer. Intersystem crossing is a process that takes time, so delayed glowing is generally phosphorescence. Mostly what we care about is these band gaps. So the energy between HOMO and LUMO, the energy here, to take this up to here, is going to have to do with the energy it takes to go from here to here, right? That energy gap, there we go. That energy gap gets smaller when we have more double bonds. If we just have more double bonds, it'll get a little bit smaller. When we have conjugated double bonds, it gets a whole lot smaller, right? Part of this, we can just sort of see, like, they're showing you because there are more lines. There are more lines because, see, you can either have a node or you can't, right? Here you can have one node, you can have two nodes, or you can have all three nodes. This one, there's a lot more possibilities, right? So there's a line for each possibility of how many nodes you can have. And it pushes your HOMO-LUMO gap closer together. The closer it gets, the more likely you're going to be absorbing in the UV or visible range, because lower energy wavelengths are high, or lower wavelengths, lower number wavelengths, smaller wavelengths. Smaller wavelengths are higher energy, right? Higher, larger wavelengths are lower energy. And we can remember that because, well, if we're actually looking at the light, like a light that is that wavelength, red is over here, purple's down here, which can be called violet, UV is below purple, and UV is what gives you skin cancer, right? Because it's too high energy for our skin to be okay with it. Mostly because it's very high energy light that can start breaking bonds in radicals and making radical chemistry happen. And we don't like that. So, if you want your compound to be colorful at all, you want to narrow that band gap as much as possible so that your absorption starts creeping out of the UV range and into the visible range. And even still, you don't often get past about here-ish with organic compounds a lot of the time. What I showed you here, promoting this guy with these HOMO-LUMO, this is a pi to pi star transition. So we took an electron in a pi bonding orbital, promoted it to a pi antibonding orbital, pi to pi star. There's another kind called N to pi star. That's basically if you have a ketone, basically it happens with ketones. I guess it could happen with some other stuff too, but it is basically ketones. What you end up doing is not taking one of these pi electrons and promoting it, but you take one of these, not antibonding, but non-bonding. So you take one of these lone pair electrons from up here, so N, non-bonding, not antibonding, non-bonding, one of these guys, and you promote it up to an antibonding orbital. And you get a little, 180, so like, you don't get a whole lot, you don't get very, or at all, into the UV range with this. But if you conjugate that, you get more measurable. And if you put one of these next to a benzene ring, you get an even higher wavelength. So you're pushing that band gap smaller and smaller. By the time you're conjugating this, though, you're back in the realm of pi to pi star, so N to pi star is not as useful for us at the moment. If you do photochemistry, that's not entirely true. trying not to lie to you, and I am a photochemist, but we care mostly about pi to pi star. We'll do that. Okay, conjugation and absorption. We absorb higher wavelengths of light when we have more conjugation, right? And that's because we're pushing that band gap, the HOMO and LUMO gap, closer and closer together. So higher wavelengths, lower energy, we can absorb lower energy light and still move this electron up, right? If we've got more and more conjugation. Yeah? Okay. Oh, and there are, I want to say that there's one of these has a nice little, couldn't find it, don't care anymore. The ranges of visible light and UV light. UV is somewhere in the like 200-ish to 400-ish. Maybe a little lower than that, but I think usually 400-ish is where we kind of stop UV and start visible light. Visible light is 400-ish to 650, maybe up to 700 depending. I think it's supposed to be more like 650. And then higher than that you get IR, or at least near IR. We've got like